Hello, thank you for joining this session. My name is Rohini Gaonkar and I'm a Senior Developer Advocate. And in this session, we will learn more about AWS Fault Injection Simulator, a new fully managed chaos engineering service. We will start with a little bit of information about distributed systems and why chaos engineering, which is relatively a new discipline that is emerging as a good solution in dealing with complex distributed systems. We will look at typical challenges our customers face and why they wanted us to create a chaos engineering service. Its features, the concepts, and of course, some interesting demos to get you started. While the benefits of distributed computing are undeniable and have revolutionized IT, they do have some challenges. Challenges with distributed systems involve latency, scalability, reliability, resilience, concurrency, designing the APIs, the marshalling and unmarshalling of data, and the complexity of algorithms. As systems grow larger and more distributed, what is often only a theoretical edge case can sometimes turn into a real-world occurrence. While most people understand that distributed systems are complex, it is a common mistake to think that this complexity only applies to applications that have hundreds or thousands of microservices. And that is, of course, not the case. In fact, even simple applications are complex. Take, for example, a simple client-server communication. Here, a lot of steps involved to successfully complete one single round trip. The client puts a message onto the network delivers the message to the server validates the message, updates its states, and puts a reply back onto the network. The network then delivers a reply to the client validates the reply and updates its own state. It's mind-boggling to consider all the permutations here where any failure can happen in this simple distributed system, especially over multiple requests like thousands or millions of requests happening concurrently. Now, the traditional way to tackle this challenge has been testing. But as distributed systems have grown more complex, testing has reached its limits. And often, we only implement tests after an outage has happened in our production environment, which of course is too late. Now, testing is of course mandatory and you shouldn't stop doing it. But it doesn't apply well for all distributed systems and often doesn't address the complexity of production environments. Testing tests things in isolation and it also tests or verifies known conditions. What about random failures and other weird errors that can happen over our networks like the internet? How about configuration limits or configuration drifts? What about the unknown? How can you test something you don't know yet? And some things are just really hard to test. For example, in a system where instances start and stop dynamically, what happens if any of the instances actually runs out of a disk space? And I'm pretty sure a lot of us have faced disk space errors or failures in some form or the other. And debugging applications that run out of disk space may look something like this. It is relatively a common issue that happens when no log rotation is there. And to make things more complicated, you can get a no space left error when there is plenty of space on the device. So for example, when the file system has run out of inodes because too many files have been created. The problem with disk space failures is that it is localized and isn't something that you can catch during testing. So what happens when you have disk space failures? If your instance does not have space left to write, it most of the times fails so fast that it creates a black hole, probably fooling your load balancer into thinking that the instance is free to receive requests, which in turn will further fail. So if we could catch these issues earlier, we could have made some improvements in the system before they actually became outages. And in this case, the improvements could be adding a log rotation or using a centralized logging service or adding monitoring of disk space that whenever there is 10% or 20% of space left, raise an alarm. And this would give some time to us to act before an outage happens. Luckily, there is a practice that helps with this kind of unknowns and it is, as you probably guessed, chaos engineering. Chaos engineering is the process of stressing an application in testing or production environment by creating disruptive events like a server outage or an API throttling. then observing these disruptive events on how our system responds to these events, and then implementing improvements to our overall system. And we do this to prove or disapprove our assumptions about our system's capability to handle these different disruptive events. Rather than letting these disruptive events happen in production at 3 a.m. or on a weekend, we can create them in a very controlled environment during our working hours when everyone would be available in the office. It is also important to note that chaos engineering is not just about improving the resilience of your application, but it also helps in improving your performance, uncovering certain hidden issues, exposing your blind spots in your monitoring, observability, or your alarming systems, improving your recovery times, operation skills, and even the culture of your team. It is also very important to understand that chaos engineering is not about breaking things randomly without a purpose. It is about breaking things in a controlled environment through well-planned experiments in order to build confidence in your application and tools that you're using to withstand the turbulent conditions. Now, to do that, you have to follow a well-defined scientific method that will take you from understanding the steady state of your application, articulating a hypothesis, running an experiment, often injecting a fault into your system, verifying the results, and finally learning from these experiments in order to improve your overall system. However, while chaos engineering is a great tool to have in your toolbox, a lot of our customers have told us that they feel it is hard to get started with. And it's hard because currently you have to stitch different tools, some scripts and some kind of libraries to be able to cover the full spectrum of faults that you can ingest into your system. The infrastructure, the network, the application, each have different tools to do jobs, whether it's a library or an agent. Customers often don't want to install anything extra in their application because more things to install equals more complexity, and it is also difficult to ensure a safe environment in which to inject these faults. Ideally, you would also want these to nicely integrate with your monitoring solution. You would want your tools to automatically stop and roll back to your steady state if any alarms are setting off. And finally, some failures are simply really hard to reproduce. It is important to realize that outages rarely happen because of a single failure. It is often a combination of small failures that are happening at the same time or maybe in a sequence, one after the other, and this is something really hard to reproduce. So today, I am really excited to announce you to our service, AWS Fault Injection Simulator, a fully managed chaos engineering service. It is an easy to get started service which lets you reproduce your real world failures, whether they are simple failures like unresponsive or stopped in servers or more complex like throttled APIs. And Fizz fully embraces the idea of safeguards, which is a way to monitor the blast radius of your experiment and stop it automatically if an alarm is being set off. So let's see each of these in detail. Now, getting started with the service is very easy, and this is something we have put a lot of effort into since our customers have told repeatedly that it's hard to get started with chaos engineering. So you can use the console to get familiar with the service, and then you can move on to CLI to take advantage of the templates and integrate the service with your CI/CD pipeline. Now, the templates here can be JSON or YAML based files that you can share with your team, do version control, or make use of all the best practices associated with code review. You can run your experiments in sequence or in parallel, where in sequence you can use that to test the impact of gradual degradation, like sequence of actions that are gradually increasing the latency of our application. And parallel experiments are to test the impact of multiple concurrent issues, which is often how real-world outages happen. Today, it supports services like Amazon EC2 or RDS, ECS, and EKS, and more will soon follow. So you can create complex conditions that span across a large set of AWS services. Just to hit the nail on the head here, please note that these faults are really happening at the service control plane. So when you run these experiments, an instance is actually going to be terminated, memory is actually going to be utilized, or an API is actually going to be throttled. It is not faking it with some kind of metric manipulation. So please use extra caution when using this service. And to ensure safety, the service provides a lot of safeguards for us to use. They act as automated stop buttons. It is a way to monitor the blast radius of the experiment and make sure that it is contained and the failures created with the experiment are rolled back if certain alarms go off. Now, FIS integrates with IAM roles and policies, so you can be sure that only authorized parties can run experiments, and you can also define more fine-grained controls. For example, what type of faults are authorized on which kind of resources. Here, you can see the architecture diagram of the service. When you create your chaos experiment from the console, FIS automatically creates a template for you, which you can then reuse later. We already talked about the fine-grained controls with IAM. Once you start your experiment, FIS injects the real failures on your AWS resources. And it is a best practice to have CloudWatch alarms monitoring these resources and defining some kind of stop conditions that will automatically stop the experiment if that CloudWatch alarm status changes. Finally, you will be able to integrate your own monitoring solutions via EventBridge in order to trigger the stop conditions. To use the service, you only need to understand 4 components: actions, targets, experiment templates, and the experiments. So let's look at each of these in detail. Actions are the fault injection actions that are going to be executed during an experiment on your target resources. So you must specify at least one action in your experiment template. Now this is a JSON representation of your actions. Here you have 2 different actions defined: stop instances and wait. And notice that wait is ordered to execute after the stop instances, and hence this is a sequential experiment execution. It is worth noting that some host level actions on EC2 instances are performed through AWS Systems Manager agent. The SSM agent is an Amazon software that is installed by default on most Amazon Linux and Ubuntu images. And I will definitely show you the integration in one of our demos. Targets define one or more AWS resources on which to carry out the actions defined. You can define multiple targets in your application, or you can use the same target for multiple actions. In this JSON representation of your targets, you are using filters to target instances that are only in the availability zone US East 1A or a particular VPC. But that's not the only filter here. Notice the use of tags to actually refine your selection. And this is a best practice to use tags where instances that are tagged with purpose as chaos ready will only be targeted. This is another safeguard mechanism to prevent any mistakes. Experiment templates define an experiment and are used in the start experiment request. And this template will include actions, targets, stop conditions, your alarms, your IAM roles, your description, and tags. In the demos, we will see how to define these experiment templates via the console and via CLI. So a template looks something like that. And again, you can use JSON or YAML as you prefer. You can have the name using tags, the description, the IAM role, the stop conditions, the targets, and finally the actions that are to be performed on these targets. An experiment template contains one or more actions to run on the specified targets during an experiment. It also contains the stop conditions to prevent the experiment from going out of bounds. After you create an experiment template, you can use it to run an experiment. As explained earlier, you can run simple experiments like the one on the left, which is a sequential experiment with specific targets, or you could have more complex experiments running in a mix of sequences and parallel executions and using advanced filtering for your targets. For both, I strongly recommend using alarms in test and especially in your production environments. It is the best way to really benefit the full power of your service. We will also see how to define these via the console in the upcoming demo. Finally, experiments are simply a snapshot or an instance of their experiment template when it was first launched. So it is your history of experiment execution, and it includes information about the creation and start time, the status, the execution ID, the experiment template ID, and the IAM role used. Here are some of the faults that we are bringing in for the service, with more to come. We love hearing feedback from our customers, so play with these, and if you want more, just send us a note. Now let's check out few demos for the features. Let's start with a simple experiment in the console, get into more complicated one into the CLI. So in the first demo, we will use the fizz experiment to randomly stop a running instance in a controlled environment. When you log into the AWS Fault Injection Simulator in the AWS Management Console, this is what the dashboard looks like. You can find all your experiment templates at the experiment template section, the actions that are supported by the service today, and the different services that it supports for, and finally the experiments that you have executed or run before. So let's go back to the dashboard, click on Create Experiment Template. Here, let's provide a description for our experiment template. Let's call it Stop and Start Instances and define an IAM role. You can find more information in the documentation on how to define this IAM role. Click on Add Action, provide it a name such as Stop Instances. We'll leave the description as optional. Write action type as AWS EC2 Stop Instances. Then you can see that a target is automatically created for you. We will check this out later. Now here we will give start instances after duration of 1 minute. Go ahead and save this action. You can see that stop instances action has been created and it will start at the beginning of the experiment, and the target is instance target 1, which you can see is automatically created for you. Now here let me show you how you can create sequential or parallel actions. Let's create a new action called as terminate instances and use the start after option to mention if you want to start this action after the stop instances action. Notice how it says start at the beginning for stop instances and start after stop instances for terminate instances action. Now if I want to execute both of them parallelly, I just remove that option and see that both will start at the beginning of the experiment. In this way, you can create more complex actions by adding or removing actions. Let's remove this action because I only want to show you the stop instances one. In the target section, here it's already created, so click on edit and then you can see the different resource types that are supported by the service today. Here either I can provide the resource IDs by selecting each individually, or I could provide tags and filters where I can say select all or select a certain number or select certain percentage of the resources that you will be defining. So let's say I'm selecting 2 resources of having key experiment and a value as chaos ready. We will leave filters for later demo. Save this and go ahead and save your experiment. Once you click on create, you will get a notification that you have not defined a stop condition for your experiment template. Is this sure that you want to create this experiment? This is to ensure that you use all the best practices. Now let's check out the different things that we have already created, test it, okay, everything looks great, and then go ahead and check whatever options we have selected look perfect. Use this experiment template ID if you are using CLI to start the experiment. Now let me show you that yes, all the instances are running. I have 10 instances created and they are running in 2 different availability zones and they do have tagged as experiment and chaos ready. All the instances are running fine. So let's go ahead and start this experiment. Click actions, click start. You can give any experiment tags if you want, and you will have to actually all the time mention that you want to create these destructive actions. These are all safeguards that we have added into the service. Right, start and start the experiment. You have successfully started the experiment. You can see that the state is running. You can also see individual action state as well, which is currently in pending mode. Let's see our EC2 instances and refresh. And you can automatically see there are 2 instances have already in stopping state. So depending on the experiment that we define, we can already see that 2 instances are stopped from this experiment. But then we also said that start the instances after a duration. So we will start the instance automatically after a minute. So let's go back and fast forward a minute later. And you can see that 2 instances that were stopped are now automatically in your pending state, that is, they will go into a running mode. And when you refresh the experiment, you can see that the status of your experiment has changed to completed. In the next demo, we will see how to add alarms to that experiment and ensure a safe rollback. In the same experiment, notice we didn't provide any stop conditions. So let's go ahead and update the experiment template. Here, notice I have already given that it should start after 5 minutes. And I'm going to just go ahead and add the stop condition for network in abnormal. So if this alarm is triggered, the experiment is stopped. Yes, we have now defined a stop condition. Let me quickly show you the EC2 instances. Yes, all the EC2 instances are in running mode. Our alarm is in an OK status, and we will now start the experiment. Again, confirm that you are doing this disruptive activity. Start the experiment and you can see that it is again in a running status, and it's obviously pending mode because it's doing activities on our EC2 instances. Yes, our EC2 instances are stopping. Let's refresh again and see that yes, the instances are now in stopped state for the next 5 minutes. Now what we will do is, in this experiment, we will manually change this alarm status from OK to alarm, because this is not really my environment. So I'm just going to do this to show you how we can see the rollback happen. Once you do that, refresh the CloudWatch alarm and you can see that it has gone into an N alarm state. So what should this do? This should actually stop the experiment. Yes, the experiment was stopped because of the stop condition. And you can see even the action was stopped. So what should happen in this case? We should go back to our steady state. And the steady state is all instances are running. This means our experiment has easily rolled back to the steady state. In the next demo, we will use the CLI to define the template and start the experiment. We will also add filters to showcase common chaos experiment of an availability zone outage. Until now, we saw all the experiment templates and experiments being created via the AWS console. In this demo, we will use the AWS CLI to actually define an experiment template. Note that I just have one experiment template been defined here. When you have to create it via the CLI, you have to define a JSON or a YAML based file with a particular name. Here we have defined in JSON format, we have given it a name, we have provided description, we have provided the stop condition alarms that we want to define. We have also defined actions and targets. In actions, we are using the AWS EC2 stop instances action and provided the parameters required. In the target sections, we are referring to the 2 stop instances targets. We have provided the resource type, the tags to be experiment and chaos ready, and further we have also provided filters where any instance matching these filter criterias will now be stopped by the experiment. So they should be in the availability zone 1B, they should be running, they should be part of the VPC that we have defined. Now I'm assuming that you've already installed and configured your AWS CLI. So let's run the command AWS fizz, create experiment template, and provide the file that we just saw, the JSON file that we just saw, as a CLI input for this command. Press enter and it will return the value as the experiment template ID and the other details that you've provided in the template itself. Copy with the template ID because that's going to be needed in the next command. Let's refresh and see if it is visible in the console. Yes, it is. For making sure that we are going to do these disruptive activities, we're just going to check if the parameters are correctly visible in the console as well. Yes, the actions, the targets, the resource tags, the filters, Everything looks great. So let's go ahead and start this experiment via the CLI. Write the command AWS fis start experiment and provide the experiment template ID we just copied. When you press enter, it will provide you the experiment ID, the template ID, the status of this experiment, etc. Just copy this ID and let's see this in the AWS console for simplicity. Yes, the experiment is running and the action is also in progress. Let's head over to that EC2 console and see that yes, I have instances in all the 3 ACs. The moment I do refresh, you can see that the instances that were matching the criteria are now stopped. And this is how you can simply simulate an AZ failure and see how your system responds, what kind of alarms are being raised, and how you can improve the resiliency performance of your entire system. And in the final demo, we will look at little advanced use cases. We will use an AWS Systems Manager to send a command to our EC2 instance and increase its CPU as a disruptive event, and watch the automated alarms trigger a rollback of your experiment. In this experiment, before we create the experiment template, let's head over to the AWS Systems Manager console. Head over to Documents and search for fis. You will find that AWS has already defined few fis templates for you to quickly use in your experiments. For this demo, we will use the AWS fis run CPU stress, which uses the stress ng tool to stress your CPU on the targets. It has 3 parameters for the duration of the experiment, the CPU that you want to target, and the dependencies to be installed, if any. Let's confirm there is no experiment been created. So for the CLI, we will define a JSON-based template called as fis SSM demo, which provides an integration with SSM. The action is here going to be AWS SSM send command. Here we are mentioning the document ARN of the document we just saw in the console, and the duration we are saying is for 5 minutes. There is also targets been defined as an EC2 instance. So I've defined my instance in the resource ARNs. I've also defined stop condition, where if the abnormal CPU alarm is raised, you have to stop this experiment automatically. Notice, if you want to define your own document instead of the AWS provided one, you can write your own document, upload it to SSM, and then just simply update the document ARN here with your own document. So let's head over to the CLI and create the experiment template with the file we just saw. Note the experiment template ID because we will need it to run the experiment. Let's check this out in the AWS console and verify that everything looks perfect before we start the experiment. Yes, the actions look great, the duration seems perfect, and the instance is the target instance. So let me also confirm the source ARN. Yes, the instance looks correct, and I've also defined the stop condition. Let me also check the CloudWatch alarm if it is in OK state. Yes, the CloudWatch alarm seems to be in the OK state. Before we start the experiment, I also want to log into this EC2 instance and run htop so we can see if the CPU is being stressed or not. So let's quickly start the experiment using the template ID we just copied. Of course, you can also find more information here, or just copy this template experiment ID and paste it in the AWS console. You can find all the details that yes, it is running, it has been initiated. And does our alarm look okay? As of now, not really much update. So let's see the EC2 instance. Yes, the CPU is at 99% or so, and the command is running on that EC2 instance. So let's fast forward a bit so that CloudWatch can catch up and check the alarm status. Yes, we can see that CPU utilization has now increased. And here the alarm has been defined to be anything greater than or equal to 50 for a minute, the alarm should be raised. Wow, the alarm has automatically been raised. So what should happen in this case? Yes, you're right. The experiment should automatically be stopped. And that's what the state defines. The experiment is stopped because of the stop condition. And the action should also be stopped in this case. Let's confirm this quickly on the EC2 instance. Yes, there is no command running. If you want to find more information about this, you can go to the run command history and find more information of the status being cancelled in this case. We hope you found this session helpful and you can use this information to get started with your chaos experiments.